In this video, we're going to start talking about acid and base strength. So not all acids donate protons to the same extent. So acid and base strength. And be really careful when we refer to an acid or a base as being strong. What we're talking about is the extent that it dissociates or ionizes, right? If we want to think about Arrhenius theory, a strong acid, and I will write all this down here in a few minutes, but a strong acid is going to dissociate or ionize completely, right? If I have HCl, it's going to completely separate into hydrogen ions and chloride ions. A weak acid is not going to completely ionize. It's only going to ionize to a smaller extent. Acid-base strength has nothing to do with its corrosive abilities. So you can have something that's called a weak acid that's actually much more corrosive as far as eating through things than a strong base is. So when we're referring to acid-base strength, please note we're just referring to the extent at which it dissociates or ionizes. So a strong acid this ionizes to a large extent. And what we're going to actually refer to it as, it ionizes completely. There's often a small amount that's not ionizing, but we're going to ignore that small amount. So for all practical purposes, a strong acid is going to ionize completely. That's the word that I want us to use. So essentially 100%. Hydrochloric acid is a strong acid. I'm just using Arrhenius here. I'm putting it in water, and I end up with hydrogen ions and chloride ions. Right? Notice how I'm not writing a reversible arrow. The arrow is going just to products. So every little bit of it, right? If I was to draw a beaker of hydrochloric acid, I have water because we're putting it in water. I have hydrogen ions and I have chloride ions. I do not have any HCl in that beaker. If you remember your solubility rules for 150, 151, right? These are strong electrolytes. They're dissociating completely, ionizing completely. Remember, we're trying to get in the habit of using the word ionize because this is not ionic, right? We're making ions out of something that was not ionic. So we're ionizing it. Something that is weak, right? A weak acid this ionizes partially, so to a smaller extent. And partially is how we usually say it. So does it completely ionize? Does it partially ionize? An example of a weak acid, hydrofluoric acid is weak. It is going to ionize into hydrogen ions and fluoride ions, but that actually goes back to form hydrogen fluoride or hydrofluoric acid since it's an aqueous solution, right? If I was to draw a beaker with hydrofluoric acid, I'm going to have water, I'm going to have hydrogen ions, I'm going to have fluoride ions, and I'm also going to have hydrofluoric acid. Right? Here, I just have the ionized form because it's strong. It's ionizing completely because it's a strong acid. With this one, I have both the ionized form and our covalently bonded form because it's ionizing only partially because it's a weak acid. Are weak acids typically ionized to about 5%? So if I go back to my beaker here, I would have about 5% of it in that ionized form and about 95% of it in that covalently bonded form, right? Because this is reversible, it can exist at equilibrium, right? When the rate in the forward direction and the rate in the reverse direction is equal, they are at equilibrium. So I can write an equilibrium constant expression for this, right? And since 95% of it is in the form of my reactant, I am going to have small values, right, for my equilibrium constant. My percent for strong acids, because we're saying completely, we're going to assume 100%. I keep putting the about there because there is a small amount, but for us, and not just us, most classes, we're going to just say 100%. We do need to know which acids are strong and which are weak, and the easiest way to learn those is to just memorize the strong acids. There's only 7 of them, so if we memorize the 7 strong acids, every other acid I give you is going to be weak. And it is going to be important to be able to differentiate between the two. Once we start talking about pHs, we need to know, right, does our reaction just go in one direction? Or does the reaction exist at equilibrium? And to be able to tell, we need to know, is it a strong acid or is it a weak acid? So again, there's 7 strong acids, so it's not a huge list. Some of you may have been asked to memorize them in 150, 151 already. So you do need to learn these, memorize. If you remember them, it would be kind of a cool test to see if you can jot them down. So hit pause, see if you can remember any of them from your chemistry past, and then hit play again to check. If you don't get all 7, that's okay. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid, which is kind of weird to say. I have nitric acid, chloric acid, and then perchloric acid. All of these are in aqueous solution. Remember HCl, it's not hydrochloric acid until it's an aqueous solution, right? Just HCl, if it was a gas, it's hydrogen chloride, right? It's not until I put it in water and it ionizes that we call it an acid. And then one more, sulfuric acid. And it's actually only the first proton that's strong, right? It has 2 protons that it can lose. Remember, its conjugate base is going to differ by 1 proton. So going from H2SO4 to HSO4 minus is strong. HSO4 minus is not a strong acid. I'm not writing that on my list. So losing that second proton is weak. So please learn these. If we were writing reactions with these, I'm not going to write reversible arrows, or I'm not going to write equilibrium arrows. I'm not going to have equilibrium constant expressions for these. They are going to be 100% for all practical purposes dissociated in aqueous solution. Looking at a reaction, kind of using the Bronsted-Lowry perspective, right up above I was looking at Arrhenius. Bronsted-Lowry, I need to have a base for it to react with, and water is what's serving as that base, right? I am putting them in water. I'm only going to draw an arrow in one direction, and my acid is going to donate that proton to water to give us hydronium ions, and then I'm going to be left with Br minus. So this is my acid. Water is acting like a base. Water can act both like a base and an acid. This is my conjugate acid, and then this is my conjugate base. Remember, acid-base pairs are going to differ by 1 proton and only 1 proton. Water is a pure liquid, and then all of these others are in aqueous solution. They're in water. And honestly, this is the better way to write it. If we go up to these beakers, I don't actually have protons in water. That hydrogen ion is going to attach to water. So H plus and H2O actually is H3O plus. So even when you're writing it, using Arrhenius, this isn't particularly accurate. A proton in water doesn't really exist. A proton in water is going to form hydronium ions. So kind of the better way to draw these beaker drawings and how we're going to draw them most of the way from here on out. I have water, I have hydronium ions, I have my conjugate base, right? This one, I have water, I have hydronium ions, I have my conjugate base, and then I also have my original acid because it's only partially ionized. That, again, being the better way to write it. Protons in water don't really exist. And to be completely honest, hydronium ions probably bond to another water molecule, and you end up with like H5O2. They kind of tend to bond to each other, but hydronium H3O plus is much better than a proton in water. So this really is, kind of the better way to write it. Again, do note that my arrow is just going in one direction, right? It's completely ionized. Looking at the conjugate base, right, because hydrobromic acid is completely ionized, right, my arrow is just going in one direction. Bromine, even though it's my conjugate base, is not really basic. It's not going to accept a proton and go back in the other direction, right? I would not write bromide ions plus some sort of acid going back to hydrobromic acid plus water, right? I'm labeling it as a conjugate base, right? It differs by one proton from my acid, but it's not actually basic. We're gonna put a big red X right through this, right? This wouldn't happen. We can say that my conjugate base has no affinity, right? It doesn't want to bond to for protons. And that's going to be true for the conjugate base of any strong acid. So the conjugate base of a strong acid is not actually basic. We would say that it's inert, meaning not reactive, right? It's not going to take a proton and go back in the other direction. We're still labeling it as a conjugate base, right? By definition, it still differs from HBr by one proton and one proton only, but does it function as a base? Is it going to accept a proton? No, it isn't. So the stronger your acid, essentially the weaker your conjugate base. So if it's a strong acid, then the conjugate base is not really basic. Looking at a weak acid, we'll use hydrofluoric acid again. I am going to react it with water. Water is going to act like a base in this case and accept that proton. And I'm going to form hydronium ions plus fluoride ions as my conjugate base. And this time, right, it is a reversible reaction. HF can give a proton to water to produce hydronium and fluoride ions, or hydronium ions can give a proton to fluoride ions to go back and produce hydrogen, hydrofluoric acid and water. So the conjugate base of a weak acid is basic, right? It does go in both directions. So let's label these here. This is my acid, water's acting like my base, my conjugate acid, and then my conjugate base. In this time, right, the conjugate base does accept protons, right? It is basic. So the conjugate base of a weak acid is a weak base. So it's an inverse relationship, right, between the strength of the acid and the strength of its conjugate base. I just want to add weak to this one, or sorry, strong to this one. We know it's strong even if I didn't label it, right? How we know that is I just have an arrow going in one direction. And then this one we know is weak. We know that because I'm going in the forward direction, but then also, right, fluoride ions can take a proton from hydronium ions and go back in the opposite direction. Looking at some bases, we're also going to categorize those as either being strong or weak. So strong bases, kind of the same sort of definition. A strong base is going to be a strong electrolyte. These are going to be species that do dissociate essentially completely, for us, we're going to say completely, in aqueous solution. So strong bases dissociate completely, right, to a larger extent in aqueous solution. Again, I'm really just looking at the Arrhenius theory when I wrote it that way. If we wanted to look at Bronsted-Lowry, it is going to accept, right, all molecules of base in our sample, right, in our solution are going to accept protons. As with the acids, the easiest way to learn the strong and weak bases is to just memorize the strong bases. Any other base I give you will be a weak one, and there's going to be 8 strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide, rubidium, and then also calcium hydroxide, strontium, and barium. If you were to look at your solubility rules, all of these are soluble, right? They're all strong electrolytes. They're ionic substances. Remember, if it had a group 1A cation, which is what all of these ones in the first list are, they were going to be soluble in aqueous solution. There was no exceptions. And then on the hydroxide side, we said that often they're insoluble unless it's with a group 1A cation or the calcium, strontium, or barium exceptions. So do memorize these. There are actually other strong bases. If you have NH2- as your anion, it's actually stronger than OH-. Carbon with a negative charge is also strong, but these are the ones that we're going to stick to for this class. So memorize these. If you go on to organic, we are going to give you a couple new strong bases also, but we will stick to these. Again, they all have hydroxide in them, so they're pretty straightforward to memorize. So hydroxide ions in a group 1A cation, and then kind of just really 3 others that you would need to remember. So again, if you have any of these are going to separate completely in aqueous solution. So if I had a container, and let's use calcium hydroxide as my example, I have water, right? It's an aqueous solution. Calcium has a +2 charge, and then looking at our formula for calcium hydroxide, I do have 2 hydroxides for every 1 calcium. So drawing calcium hydroxide in water, this is what my beaker drawing would look like. Weak bases then. These are going to dissociate partially to a smaller extent. couple examples for us. Often they'll have nitrogen in them. And again, you don't really need to memorize these. I'm just giving you some common ones. The easiest way, again, is to just memorize the strong ones. And then if it's not one of those. So nitrogen bonded to 3 hydrogens. Or we could have, I'm going to kind of rewrite this. I could have nitrogen bonded to 3 R groups, where R is either going to be a carbon-based group or a hydrogen. So if you see, CH3 with a 2 and then a hydrogen on there, that is kind of this example, right? I have nitrogen bonded to 3 groups. It's bonded to a hydrogen and 2 CH3 groups. So nitrogen bonded to either carbons or hydrogens, and there's 3 of those. And then any conjugate of a weak acid, right? We said that the conjugate base of a weak acid is basic. So like fluoride ions is a common one, HF is weak. We could look at, like carbonic acid is a weak acid. So carbonate, not carbonate, right? Hydrogen, carbonate, so bicarbonate, all of those. So any conjugate of a weak, any conjugate of a weak acid is going to be a weak base, right? We talked about that up here. If I wanted to draw a beaker drawing of my weak base, and we'll just use NH3 here as our example. I have water, I have some NH3, and then I also have, and we can draw some reactions here, I have its conjugate acid, NH4+. Right? Where I'm getting that is if I take this, right, and I react it with water, I do have a reaction that can go in both directions. I end up with NH4+, my conjugate acid, and then water in this case is acting like an acid. So I actually end up with its conjugate base, which is hydroxide ions. So going back up to my beaker drawing here, I would add some hydroxide ions to it. So this is my base. Water is acting like an acid this time, right? We had said that it can react like an acid and a base. This is my conjugate acid, and then this is my conjugate base. And then looking at that conjugate acid, it is actually acidic, right? The conjugate acid can donate its protons, right? This arrow is going in both directions. So ammonium ions can give that proton back to hydroxide ions to form ammonia in water, right? The conjugate acid of a weak base is a weak acid. So just kind of comparing here, right? If I have a weak acid, its conjugate base is basic. If I have a weak base, its conjugate acid is acidic. If I have ones that are strong, right, I'm only going in this one direction. So my conjugate is actually not basic. In fact, sometimes you'll just say it doesn't have a conjugate base. Technically that differs by 1 proton, so it is a conjugate base. If I asked you to label acids, bases, conjugate bases, we are going to label it, but it's not actually going to serve the function of a base by taking that proton. If we wanted to actually write an example for this, right, I'm taking lithium hydroxide, and I'm using a different base here instead of calcium, like I did in my beaker drawing. It's an aqueous solution. And we're dissociating it, right? We're separating those ions to produce lithium ions separate from hydroxide ions, right? Just going in one direction. And I actually really don't have conjugate acids here. I know it's kind of weird. If I wanted to write it by putting water in, right, lithium hydroxide plus water, I'm really just getting lithium ions plus hydroxide ions plus water. So you don't even think of this one as having a conjugate acid. So strong bases, strong bases, do not have conjugate acids. I have a table here with some acids and bases on it, and I know this is kind of hard to read, but this is kind of what I want to draw our attention to. It says increasing acid strength. I'll write it a little bit bigger here. So increasing acid strength. Right? Just because something is a weak acid doesn't mean it's equally weak, right? Be really careful to differentiate between a strong acid, right? Something that ionizes completely, and a stronger acid, right? For example, if I look here, I have nitrous acid and acetic acid. They're both weak acids, but nitrous acid is a stronger weak acid than acetic acid is, right? Not all weak acids are equally weak. Some are stronger than others, right? Stronger acids are going to ionize more. So nitrous acid is going to ionize more than acetic acid would. It would actually have a larger value for its equilibrium constant, right? Because I have more products relative to acetic acid. So be really careful. If I say stronger acid, I'm not necessarily meaning strong acid. I just mean an acid that is dissociating more. If I look on the other side, increasing base strength, and this time my arrow is going down. It's opposite. So increasing base strength. Right? It gets stronger base as I go down, a stronger acid as we go up. Remember that those two, right, the strength between an acid and its conjugate base are inversely related. If I look, these are my strong acids, and we know that because we are going to memorize that list, but also it says it undergoes complete ionization in water. And then if we look on the other side at its conjugates, right, these do not being a keyword here, undergo ionization in water. So these ones, right, we say they have no affinity for hydrogen ions, right? Remember, the conjugate base of a strong acid is not really basic, right? It's not going to take a proton and has no affinity. I do have the conjugates of weaker acids down here, and these do accept protons. So these have an affinity versus do not, no affinity. For hydrogen ions. And then looking, I'm going to highlight these two, looking at acetic acid and nitrous acid again, right? Nitrous acid is further up, so it's a stronger acid than acetic acid is. They're both weak, but nitrous acid is a stronger acid. And then if I look at the conjugates over here, right, on this side, they're bases, right, my conjugate bases. Remember, base strength increases as I go down, so acetate is the stronger base, acetic acid is the weaker of those acids. So the one with the stronger acid is going to have the weaker conjugate base. The one with the weaker acid, right, the weaker acid is going to have the stronger conjugate base. The two are inversely related. Again, I know I'm beating this to death. If it's a strong acid, its conjugate does not have an affinity for hydrogen ions. It's essentially not basic. We're going to look at some factors that affect acid strength. So why is hydrofluoric acid a weak acid and hydrochloric acid a strong acid? What is it about that molecule that makes it so?